Hi, this video is for Chem 102. This is going to be section 10.4. So this section we're going to talk about calorimetry, and we're going to start by talking about specific heat and heat capacity. So calorimetry is the measurement of heat changes. So literally we're just measuring like how much heat goes into that. We talked about this in class, endothermic and exothermic. So like how much heat is put into that system, how much heat comes out of that system. That's the measurement of that is calorimetry. We measure these heat changes in a device called a calorimeter. And we'll see some examples or some images of those devices, and you'll probably do a lab with a calorimeter, a basic calorimeter. And then the specific heat we will say is S of a substance is the amount of heat needed to raise the temperature of 1 gram by 1 degree C. And in class, we're going to look at how this is in a real life scenario, or I guess several real life scenarios, so you can get a better idea of this concept. But the more amount of heat you need to change the temperature, the higher the specific heat. So if we look at a table like this, we look at the specific heats. There's one that stands out as way higher than the rest of them. That's water. It takes a lot more energy to change the temperature of water than the rest of these things. And you probably already know that about water, that it takes water forever to get warm, to heat up, versus if you just have an aluminum pan, it has a much lower specific heat. And if you start to apply heat to an aluminum pan, it immediately is going to get hot. Heat capacity, so specific heat and heat capacity are different. Specific heat talks about the amount of the substance. So specifically has a gram in that definition. Heat capacity is just how much heat for a degree Celsius. It does not care about the amount. The object can be any given amount of a particular substance. So you'll just say like heat capacity of 1 kilogram of water. The specific heat talks about the gram, like it has a specific amount. The heat capacity of, you would just have to say, this is the heat capacity of 1 kilogram. And so if we wanted to go from specific heat to heat capacity, we have to know how much we're talking about, cancel out those grams, and just get our amount of energy in joules per degree C. So you could take specific heat and turn it into heat capacity simply by looking at the difference in your units. What are the difference in my units? One has grams, one doesn't. How do I get rid of grams? Cancel them out. If grams are on the bottom, I need to multiply it by the number of grams. A kilogram is 1,000 grams, right? So we're using dimensional analysis all the time and watching our units. All the time your units matter. So don't let me catch you with naked numbers, except for pH and there's certain constants that don't have units. So that's the big difference there. Specific heat and heat capacity can be used in formulas. So Q is equal to the specific heat times the mass times the change in temperature, where big C is the heat capacity. Q is equal to the heat capacity times change in temperature. Y'all, you don't have to think about this too hard. Joules are equal to joules over gram degree C times gram times degree C. Think about what the units are for each of these things, and that can really help you make sense of the formulas. Or what formula do I use, right? Well, look at what units we have, right? If I don't have mass, probably use this formula because this formula doesn't involve mass. If I do have mass, I gotta have that formula, right? Because I gotta use the specific heat because there's grams in there, and I gotta use the mass to cancel out the grams. So use your units to guide you to help you figure out what formulas you need to use. Delta T is change in temperature. It's always final minus initial. And you'll also see this formula used kind of, not incorrectly, but like a lot of times we might say something like this: specific heat capacity. And you may hear me say specific heat capacity. And that sometimes is denoted as little c. So we might see Q equals mc delta T as a formula to use when we really mean specific heat capacity here. This is little c, and it is used as the same as S. So you may see this formula, you may watch a video that has that formula. I think that MCAT, I don't think they give you a formula sheet, but if you take like an MCAT prep class, they may use this formula. So I don't want you to get confused if you see this little c. If it has mass in the formula, you're using specific heat because specific heat is specific for the amount of mass. That's just a way you can try to remember it. Heat capacity does not have mass in it, so it does not have mass in the formula. So let's look at this problem. What's the amount of heat required to heat 1.01 kilogram of water from 0.05 Celsius to 35.81 degrees Celsius? The specific heats, if you want them, are here. So maybe you can screenshot them or just grab the one you need. We're talking about water in this problem. All right. So go ahead and take a couple minutes, maybe pause the video to solve it. All right, this is if you have tried it. Let's see how to solve it. So we're going to use this equation because we're given mass, and then we can go grab our specific heat, which is here. Notice the unit for specific heat is grams, so we change our kilograms to grams, and then we multiply by the change in temperature. Notice that it is the final minus the initial, and we multiply by our specific heat, of course. So we're just following this formula. We get a Q here of joules, but we don't really want to represent our answer like this. It's kind of a big number, right? So we probably want to turn it into something a little more manageable, like kilojoules. For example, I don't want to be paid in pennies. Don't give me a lot of a small thing. Give me a smaller number of a larger denomination. If you have questions about solving this, definitely let me know. All right, here's another one for you to try if you want to. You can pause and try. Kind of covered up a little bit there. There you go. So again, if we're talking about water, its specific heat is 4.184. Change in temperature is the final minus the initial. And then if we're just solving for Q, the amount of heat, then it's going to be our specific heat times our mass, change in temperature, and we get this many joules. But again, that's a big number. So we'll just turn it into kilojoules to make it a little more manageable. Okay, and make sure that when you're converting from joules to kilojoules, you remember what that kilo means, and don't just have it memorized, like multiply by 1,000, divide by 1,000. Actually think about, all right, well, I know that I have to take this and I have to put the joules in the bottom because 1 kilojoule is 1,000 joules, and so I'm going to be dividing by 1,000. So do the little dimensional analysis if you need to, but you need to make sure you memorize what kilo means. All right, so you're probably going to be using a coffee cup calorimeter in lab. If you are using a calorimeter, it's probably that because it doesn't cost a lot to use those. We may be fancy enough, I'm not sure, to use some little metal cups, but coffee cups are what I always used. Just use these styrofoam cups because they're pretty good at insulating the system. Ideally, we would have a more insulated area. We don't want heat to escape our measurement. We want to measure all the heat. We don't want the heat to escape to the surroundings. But we have to make sure that we can afford for everybody to have equipment. So what we'll do is we will do a reaction and we'll measure how does the temperature change. Does the temperature go down? Does the temperature go up? And that's it. And from that, we can calculate the enthalpy because remember the enthalpy is equal to the Q. The change in enthalpy is equal to Q. So if we can measure the mass of our reaction mixture, the specific heat of the thing in this our reaction mixture, which is mostly water, and the change in temperature, then we can get Q, then we can get delta H. And so you'll be doing this in lab, I'm sure. And again, this is called constant pressure calorimetry because you're in atmospheric pressure in the lab. We're not changing pressure. So when you get up to physical chemistry, P-Chem, it will really matter if you're doing things in constant pressure or constant volume. And so we are denoting this. When we hold something constant, we put that thing kind of as a subscript. So heat at constant pressure is equal to our enthalpy change of our reaction. The system is the reaction, the surroundings is the water in the calorimeter, and the thermometer is part of the surroundings. So in an exothermic reaction, the system loses heat, so the thermometer and the water get hotter. So we see the thermometer go up, that means that the reaction was exothermic. So if I calculate an increase in temperature, that means that, so when I'm measuring the temperature, I'm measuring the mass of the whole reaction, which is including the water. I'm measuring the specific heat of the water, the change in temperature of the water. The water is the surroundings in this case. So if this goes up, then this goes up, right? This is going to be positive. So I have endothermic, the surroundings are absorbing energy, which means that the system is giving off energy. So this minus sign here is just making sure that for the system, we're doing the opposite of what we're measuring in the surroundings. And so we can write the Q of the system is the opposite of the Q of the surroundings. If the reaction gives off 10 kilojoules, the surroundings is going to absorb 10 kilojoules. That makes sense. And we will do some more math with this and talk about this more in class, but that's essentially all we're going to do in our next class session.